Alright, so now we are going to train our first bag-of-words model. In this first video, we will see how we prepare our dataset using a vectorizer. Then in the next video, we will train the actual model. So let's get started and set up our dataset here. So for this and the following code examples, we're going to work with the IMDb large movie review dataset, which is available from this Stanford website here. So this consists of a binary sentiment classification dataset where we have highly polar movie reviews. That means we have positive and negative reviews of movies, and we have 25,000 training examples and 25,000 test examples. So we are going to take advantage of that, and then here I will show you how the bag-of-words model looks like before we train a model on top of that. Of course, we start with our familiar watermark here and the imports. So notice that I already prepared a few utility functions here so that we don't have to worry too much about how we exactly download the dataset. But if you're curious, you can go to the local datasets utilities file where I have written some code here to download the dataset as a zipped file from the website. And then I'm extracting it, and then I'm partitioning it into folders and also then into data frames. So here we have then a data frame that we return, and this returned data frame consists of both the training and the test samples. So later on I have a partition dataset function where I'm partitioning it into a training, validation, and the test CSV file, which we are then loading with PyTorch using the dataset class. So this will be used in the next video. For now, we only care about the CSV files for this particular dataset. So actually, this is more like, I would say, engineering code, so don't worry so much about the data processing here. The focus is more on the bag-of-words model in this video. So the first step then, of course, would be loading the dataset into data frames using the utility functions that I just highlighted. So for that, we are going to use the download dataset function. So we are executing that. It might take a while, depending on the internet speed and the current web server speed, because if a lot of people download this, it can sometimes be a bit slower, but usually it should only take like 1 or 2 minutes. Next, we will use the load dataset into data frame function to load the texts into a data frame. So let's also do a head here where it shows us the first 5 lines of that data frame. It's always a useful thing to do so that we can double check that everything was loaded correctly. This might also take 1 or 2 minutes depending on the speed of your computer. Mostly I would say the speed of your SSD. So let's take a look at the data frame now. So we can see we have a data frame that consists of a text column where we have the movie reviews and then the labeling column here. So of course, to fit the review here visually into this table, it's only a short snippet, but we can take a look at the, let's say, full version by doing df ilog. Let's say we do the first one, the index location 1, and then let's print a text entry here. So we can see here that this is actually a pretty long text, and the label is either 0 or 1, depending basically on whether it's a negative or positive review. So a negative review will have a label of 0, and a positive review will have a label of 1. So it's a binary classification problem here. So next, let's actually partition the dataset, which will also shuffle the dataset because you can see there are only the ones here. So we want to make sure both, or all of them, the training set, validation set, and test set contain a mix of labels. And in order to make sure everything looks okay, let's actually load the training CSV, the validation CSV, and the test set CSV. So you can see, this looks shuffled, but always to make sure, it's a good idea to check the bin count, so the number of labels in this case. So we do a train, and then let's check the label column. So we expect, or we hope, this is equally distributed. And as we can see, we have approximately half of the samples from one class and half of the examples from the other class. So let's do the same thing for the validation set. And also show the bin count. And then lastly, also for the test set. Yeah, this looks all good to me. It's equally distributed here and also equally distributed here. So this is, yeah, good. So everything looks okay. So now we can then get to the back of words model. So far we were only loading the data set. Let's actually now construct the feature vectors. So for that, we need a library called scikit-learn. So you can install it, for example, using pip install scikit-learn. So scikit-learn is a machine learning library, a more, I would say, classic machine learning library that doesn't include anything, let's say, related to deep learning, but it has a lot of useful functions in there. Also a lot of useful data processing and feature, let's say, normalization and extraction methods. So it's one of my favorite libraries because there's a lot of useful stuff in there. And in particular here, what we are going to use is the count vectorizer. So if you have it installed, we can then import the count vectorizer, which helps us to create the back of words feature vectors. So here we are going to instantiate a, let's call that CV, a count vectorizer. So it's a object-oriented approach. So this is a class, a vectorizer class. And what it can do is essentially it can convert the texts here into these feature vectors which represent the word counts. In the background, when we fit this count vectorizer, it will also create this vocabulary that we talked about in the lecture. So we have a few settings here, and I will only use a few basic ones. Of course, there are more settings, but the most essential ones are essentially, in this case, making everything lowercase. I mean, this is not required, but it will, let's say, normalize the text a bit. So if we have a just with a capital letter or a smaller letter, it would map that to the same feature value or same count. So it's a little bit simpler for the model, or better, let's say, in terms of preventing overfitting if we lowercase things. But in certain cases, it might not be better. So it's, again, kind of like a hyperparameter. So then we set the number of features, the number of unique words for our vocabulary. So to prevent overfitting, I will cap that at 10,000. It will make the vectors shorter. So this will determine essentially the dimensionality of each feature vector. So it's, again, a hyperparameter. So you may want to experiment with larger values, but the larger the value, also this sometimes will lead to more overfitting and of course also consume more computational resources. It really depends, I would say, also on the data set. So something to try out and see how well it works. And then lastly, I will only use one more setting, and that is stop words. So I will set stop words here to English. And this essentially means that we are removing common words. So for example, something like the or a or this, of. So these are, I would say, like very common words, and they are not necessarily predictive of the content or not predictive of whether it's a positive or negative review. These are common words that are not, let's say, very useful for classification purposes. So stop words here means that it will strip such stop words like of, this, and the, and so forth. And so these are our settings. I made a typo here. It should be count vectorizer and not counter vectorizer. And then once we have that, we can fit this count vectorizer. So this will then build the vocabulary before we transform the texts into feature vectors. So we do tf train, and then we call it on the text. So we are fitting it only on the training data. And then we are going to transform the training data, validation data, and the test data. So let's do this fitting here. It might take a few seconds because it's 50,000 documents, or 25,000 approximately. So it's usually taking a few seconds, and then we have it fitted like here. And then let's actually take a look at the vocabulary. So the vocabulary will be the 10,000 unique words for the back of words model that is then used to create the feature vectors as explained in the lecture. So let's do the vocabulary attribute here. So this will show us the vocabulary. Oops, one typo, of course. And we can see here are all the unique words. So for example, started, the word started is corresponding to the index position 8,515 and so forth. So these are the positions in the feature vector of each of the words. And the feature vectors will be word counts as explained in the lecture. So it's actually quite a long dictionary because it has 10,000 entries. But here we can see the unique words. And these are the 10,000 most frequent words. And then next, what we are going to do is we are going to transform the training, validation, and test data. This means we are going to construct the feature vectors using this dictionary here. Again, this might take a few moments because it's a large data set. But yeah, it already finished. So, and then let's actually inspect what the dimensionality of the training vector here is, or the training matrix, I should say. So before maybe executing this, maybe pause the video at this point and think about what you would expect here as the dimensionality. So again, the number of rows would be the size of the data set, and what would you expect for the number of features? So here we have 35,000 entries. These are our 35,000 training examples. And each training example is a 10,000 feature vector corresponding to the dimensionality of this vocabulary here. Now let's actually take a look at, for example, the first training example here and see how it looks like, just to get a better feeling for it. Oh, what is happening here? So what happens here is that it is stored as a sparse matrix, which is essentially a more efficient, I would say, data storage container than a regular matrix. So a regular matrix, in contrast, would be called then a dense matrix. So this is a special data format just to, let's say, compress this to make it more efficient, because this feature vector, or each feature vector, contains a lot of zeros, and it is kind of wasteful to store all the zeros. But then, of course, it's also not very useful for us for visualization purposes. So we maybe want to convert that into a dense tensor. So what we can do is we can do the toDense method here on this first training example. And this will give us then a dense representation of, or a matrix basically, and we convert it into a NumPy array that is already familiar to us. And here, we can then see how it looks like. So this would be a feature vector corresponding to the first training example. So let's maybe call that feature vector. And we can then also, let's say, analyze it a bit more. So what would be interesting here now is what are its entries, because we can see it's kind of omitted here for, let's say, brevity, because it's a 10,000 feature vector. So it has 10,000 elements. And what are the interesting things here? So we would probably want to know what are the word counts, or what are some of the words in there. So what we could do is we could, for example, use our NumPy bin count here and call it on feature vector, and it will tell us how many entries of each kind we have. So here what we would have is we would have 9,926 zeros, 67 ones, and so forth. And these numbers, they correspond essentially to the numbers in here. So these are essentially the counts of the different words that are contained in this dictionary. So now we know essentially what the count vectorizer is doing. So we have now a way of creating these bag of words feature vectors. And in the next video, I will show you how we can then train a model based on these feature vectors, because this is essentially now our data set. So we have our 35,000 times 1,000 data input matrix, and we have 35,000 training examples that we can then use to train a model as a classifier. So in this video, we saw how we can set up a data set for training a bag of words model, which we will get to in the next video.